Welcome back, everyone. Today, we're going to be covering the theory of covalent bonding, and in this lesson, which is optional but highly encouraged, you'll learn all about molecular orbital theory and valence bond theory. I'll start with molecular orbital theory, which is a way that we can understand how electrons are delocalized across an entire molecule and give rise to new types of orbitals called molecular orbitals. In the second half of our lesson, we'll talk about valence bond theory, which helps us understand the shape of molecules and how the atomic orbitals on a specific element can hybridize to make new types of orbitals called hybrid orbitals. And these hybrid orbitals will give the correct geometries that we expect from valence shell electron pair repulsion theory. To begin with, if we look at our study of electronic configuration so far, it's revealed that the sharing of electrons in the valence shell between nonmetals allows each atom to achieve a stable arrangement, which we've been calling a noble gas configuration. This stability is due to the formation of a covalent bond where atoms share electrons cooperatively. The covalent bond has a specific energy that's associated with it that gives additional stability to the atoms so that they want to share in a partnership. The molecular orbital theory will look at the delocalized molecular orbitals, while the valence bond theory will focus on the localized overlap of hybrid orbitals. Although there are two somewhat contrasting theories, each of them offers valuable insights into chemical bonding, and we'll use them for different reasons in chemistry. So far, we've learned that with elements such as hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, that they typically form diatomic molecules under normal conditions. And furthermore, these molecules will share different numbers of electrons. So some will share 2, some 4, some 6. Why is it that they do this? Well, let's look at the Lewis structure of hydrogen to start off with. Hydrogen just has 2 electrons and they share them in a single bond. Oxygen has 12 valence electrons, and in order for each oxygen to have an octet, they need to share 4 of them, and then the other 8 electrons are distributed around the molecule. And then for nitrogen, nitrogen has a total of 10 valence electrons. So in order for nitrogen to form a stable bond, we need to form a stable configuration. We need to have a triple bond between the nitrogens. So they share 6 of them. And then the remaining 4 electrons can go on the nitrogens like this. So far, we understand a little bit about the bond order of a molecule, but when we study molecular orbital theory, we'll learn about it in a little bit more detail. And with the help of molecular orbital theory, we can also calculate the properties such as bond energy, bond length, and bond dipole quantitatively. We can see here that hydrogen has a single bond, oxygen a double bond, nitrogen a triple bond. But why do only these elements form stable homonuclear molecules? Well, other molecules don't do this, or do they do this? From our study of this topic, we're going to choose the simplest molecule, which is the molecular ion of hydrogen. The ion of hydrogen that just has 1 electron. This stable form of hydrogen allows for exact calculations of the Schrodinger equation. Although we won't be calculating those, we can compare these to other models that people have come up with. And they allow for a much simpler understanding because we just have 2 protons and 1 electron that's being shared amongst them. For a regular hydrogen atom, it occupies the 1s atomic orbital. And the 1s atomic orbital is a spherical region of space where electrons are most probably found, and this is defined by a wave function that has a radial component. So it only depends upon the distance the electron is from the nucleus. If another hydrogen atom is going to approach this hydrogen atom, the 2 1s orbitals will begin to interfere with each other because they're waves. The constructive interference between these orbitals results in a increased probability density that's between the nuclei. When the two atomic orbitals linearly combine, or we call that this superimposition, they create a molecular orbital where electrons are delocalized across both nuclei. The opposite situation can occur as well, but this constructive interference leads to a bonding molecular orbital because it increases the likelihood that that electron will be found between these two atoms. When the two atoms are at their equilibrium distance, which is known as the bond length, the wave functions are overlapped so that the energy potential is now at a minimum, meaning they're at their most favorable distance from each other. And this is the reason why bonds form, because when the wave functions overlap, they create this bonding molecular orbital. And this lowers the energy so much so that bonds are favorable. However, some bonds don't form because atomic orbitals can also destructively interfere. And because we're thinking of these as waves, if we have two waves that are out of sync with each other, they will cause a decreased amplitude in certain regions. When the region is between the nuclei, these are referred to as antibonding molecular orbitals. The reason they're antibonding is because when an electron occupies them, it has a greater probability to be found outside the space where we would expect the bond to be. This leads to a deep stabilization of the chemical bond. And these also have a greater energy than if they were in an atomic orbital. All right, so let's take a look at each of these. I'm going to introduce this new notation. So if we look at when I have two spherical 1s orbitals combining with the phases here in plus charges, combining in the same phase, it results in this cylindrically symmetric molecular orbital across the two nuclei, where the nuclei are drawn as dots on this diagram. And I have X, Y, and Z coordinates to try to indicate this is in 3 dimensions. So try to envision this as a 3-dimensional ellipsoid. And then if they destructively interfere, so if I have them out of phase and they come together, it results in a decreased probability right here in the middle. So there's a node that occurs right here. So there's decreased probability in the location where the bond would normally form. Now, because these orbitals are both cylindrically symmetric about the internuclear axis, they're both referred to as sigma orbitals. So, and then the antibonding orbital is going to be indicated with a star or an asterisk. So I'll be calling this the sigma 1s and the sigma 1s star molecular orbitals. And just keep in mind, these positive and negative symbols indicate the phase of the wave function, not the charge, because they're not charged in the same sense that an ion would be. There is a charge for the molecular ion of hydrogen, but we're not going to be indicating that in these diagrams. And then one thing to also note is that for all these diagrams I'll be showing you today, I drew the z-axis this way, so that the z-axis is defined as the region along the bond. Okay, so not the x. Some textbooks will use x instead of z. All right. Now, this figure down below shows how the energy levels of 1s atomic orbitals combine to form two different molecular orbitals, the bonding sigma 1s and the antibonding sigma star 1s. The antibonding orbital is raised in energy by approximately the same energy that the bonding orbital is lowered in energy. So I have the 1sa orbital. That's the orbital from hydrogen A. So if we define them at A and B, and then I have another atomic orbital for hydrogen B, they come together to give us two new orbitals, which are molecular orbitals. For the hydrogen molecular ion, we can fill out this molecular orbital or MO diagram by indicating that one of the atoms is going to have an electron. The other atom is not going to have an electron to share because there's a positive charge. And then that electron will automatically go to fill the lowest energy state, which will be the sigma 1s orbital right here. So this would be how you would fill out an MO diagram for the hydrogen molecular ion. From this diagram, you can see that there's a single electron, and it's now delocalized across both the nuclei in the sigma 1s orbital, and it occupies this stable state because this has a lower energy than the 1s orbital. What is the bond order of the hydrogen molecular ion? Well, the bond order is calculated by taking the number of electrons in all of the bonding orbitals and subtracting it from the number of electrons in the anti-bonding orbitals, and then dividing through by 2. Since there is 1 electron in the bonding orbital, sigma 1s, and there's 0 in the anti-bonding orbital, sigma 1s star, the equation comes out to 1 minus 0 divided by 2, giving the hydrogen molecular ion a bonding order of 1/2. So bonding orders don't have to be integer values. They can be fractions. And this is a little unusual because normally we just think of single, double, and triple bonds. But here we have a half order bond. And it is stable. We can isolate hydrogen molecular ion when we pass an electric discharge through a sample of hydrogen gas. We will get this stable ion. Let's look at a few other examples from the first row of the periodic table. We can definitely look at hydrogen, which is just 2 electrons being shared between 2 protons. These 2 electrons are going to both go into the sigma 1s orbital. Because these molecular orbitals work the same way as atomic orbitals, they can allow for 2 electrons to occupy them, and no more than 2 because they have to follow the Pauli exclusion principle. And then they also can have up and down spin, and we'll follow those principles that we've laid out for the electronic configurations, in that the lower energy orbitals get filled first, and if there's any degenerate orbitals, meaning orbitals of the same energy, both of those orbitals will get filled before they pair up. The bond order for this is going to be, well, there's 2 bonding electrons minus 0 bonding electrons divided by 2 gives us a bond order of 1. So hydrogen gives us a single bond, which is what we expect from the Lewis structure. We would write this out in its molecular geometry. We would write out its molecular electronic configuration as sigma 1s squared, where the squared indicates there's 2 electrons in the sigma 1s molecular orbital. 2 other examples we can look at for the first row are the helium molecular ion and the helium molecule. And let's see, based off of the molecular orbital theory, whether either of these molecules is stable, meaning it has a bond order that's greater than 0. And if so, what is its bond order? So to start off with, helium molecular ion is going to have a total of 3 electrons because helium each has 2, and then we remove one of them. So we'll have 3 electrons. We can put 2 of them in the sigma 1s orbital, and then the third one has to go to occupy an anti-bonding orbital. So that electron that occupies this region is destabilizing. So we end up having to subtract out one electron from the antibonding orbital to give us a bond order of 0.5, or 1/2, whichever we prefer. And this has the same bond order as the hydrogen molecular ions, so they're about equivalent in energy. Their bond lengths will differ. And we can write out the configuration as sigma 1s squared, sigma star 1s to the first. The helium molecule has 4 electrons. 2 of them occupy the sigma 1s, and then the other 2 electrons occupy the sigma 1s star orbital. Because these cancel each other out, we end up finding that the bond order for the hydrogen molecule equals 0. This means that this molecule does not exist, or it's very unlikely to exist under normal conditions. Therefore, helium prefers to just exist as an atom. And this is the same for almost all of the noble gases except for xenon, which can form some molecules. And we just completed the first row of the periodic table using this concept of delocalized orbitals or molecular orbitals. So we can correctly predict that the helium molecule doesn't exist, but it does predict a stable helium molecular ion, which we can observe experimentally. And then here are our molecular electron configurations. In fact, we can write one for helium molecule. It would look like this. All right, so let's begin to look at what happens when we make molecular orbitals from other orbitals. So we can make use of the p orbitals as well. Although the hydrogen molecular ion in its ground state will only occupy the sigma 1s molecular orbital, it can occupy additional molecular orbitals in excited states. So let's combine 2s orbitals and 2p orbitals to create some new types of orbitals. So here, to remind you, are the 5 atomic orbitals through the second shell of the periodic table. We have 1s, which is a spherically symmetric about the nucleus. The 2s, which is similar to the 1s, just larger in size. And then we have 3 2p orbitals, which exist across all 3 axes, the x, the y, and the z. And if we go to define the nuclei in the region along the z-axis, we can see, well, first off, let's look at the 2s orbitals. So the 2s orbitals will combine the same way that the 1s orbitals do. They'll just be larger in extent, and they combine to give us sigma 2s and sigma star 2s. When the 2p orbitals combine, they can combine differently, right? So if the z orbitals, the 2p z orbitals combine, they can combine head to head. So they can combine this direction, or they can combine out of phase this direction. When they combine in phase, they give a favorable bonding orbital that has a increased probability between the nuclei. So this is a sigma orbital as well because it's cylindrically symmetric. So the 2pz orbitals combine to give us the sigma 2pz, and they destructively interfere to give us the sigma 2pz star molecular orbital, which has a node here. And this node means it's unfavorable for electrons to be in this orbital. When the 2px and the 2py orbitals overlap, they do this in a different way. if we look at the 2py orbitals, it's probably easier to see based off my diagram that they don't have a region along the internuclear axis, but rather perpendicular to it. And these have a different symmetry than the sigma symmetry. These are referred to as pi molecular orbitals because they have a cross section right here that looks like a p orbital, so p pi, and they can also destructively interfere to give us 4 lobes that have 2 nodes. So there's a node along the y-axis and along the z-axis on this image here in the bottom right. And then the 2px orbitals combine the same way as the y do, just 90 degrees, creating molecular orbitals that are 90 degrees from each other. So we have 2 bonding orbitals and 2 anti-bonding orbitals again, where the pi 2px and pi 2py are doubly degenerate, meaning they have the same energy levels, and the pi 2px star and pi 2py star are also doubly degenerate. In total, when we look at all of these molecular orbitals, we have 10 molecular orbitals that came about from combining 10 atomic orbitals. 2 sets of 1s, 2s, 2pz, 2px, and 2py. And these are a mouthful to say. It can take some practice. I definitely will take some practice to get a handle on each of these. But how do each of these orbital energies compare? So I kind of talked about them in random order here. And when it really comes down to what the atomic number of that element is. When it's hydrogen through nitrogen, the order of the energy, the order of the orbital energies is this, where sigma 1s is the lowest energy, and then you have the sigma 1s star and sigma 2s star. All right, so that's pretty straightforward, and that's the same for when it's greater than nitrogen. But then for hydrogen through nitrogen, you have the pi 2px and pi 2py molecular orbitals, which have the same energy. They're the next highest in energy. Then it's the sigma 2pz. Then you have the pi 2px star and pi 2py star. And these are oftentimes we'll group these together. You might just refer to them as the pi 2p star and pi 2p orbitals, just without the x and the y. That's a shorthand. And then we have at the very top the sigma 2pz star orbital, which is the highest in energy. For when it's oxygen or fluorine or higher, the sigma 2pz orbital drops in energy below the pi 2p orbitals. So this one is lower in energy. And we can see that depicted here. So I drew all these orbitals here just to show you how they compare. Let me get rid of this. Okay, so we can see here all of our orbitals, lowest energy at the very bottom down here, and then highest energy all the way up here at the top. And then when we get to oxygen, which has an atomic number of 8, the sigma 2pz orbital drops energy below the pi 2px and pi 2py. All right, so let's look at how to make use of an MO diagram that has all of these different orbitals attached. And here is how I order all of these. So if we look at the case where z is less than or equal to 7, we have at the very bottom our sigma 1s and sigma star 1s. So this isn't any different. And then we add in our sigma 2s and sigma star 2s molecular orbitals. So those are just higher in energy. And then after that, we combine the 2px, 2py, and 2pz from both of the atoms to give us 6 new molecular orbitals. And we see the doubly degenerate pi 2p molecular orbitals and pi star 2p molecular orbitals. And then the singly degenerate sigma 2pz and sigma star 2pz. And then the only difference for this diagram over here on the right is that the sigma 2pz drops in energy below these doubly degenerate orbitals. These antibonding orbital energies stay relative to each other the same, and then everything else is the same. All right, so I like to just work through a bunch of examples on these. I think it's the easiest way to do it. If we look with diatomic lithium as our first molecule of the second period, we can determine whether this is a stable molecule or not. So for this, we'll start with all of the electrons, and then I'll switch over at some point to just looking at the valence electrons, and I'll show you why. So for lithium has 3 total electrons, and we can draw that like this. So we have 3 electrons from one lithium, 3 electrons from the other lithium on the right. And then we can go to combine the 4 electrons that are in the 1s orbitals to combine the sigma 1s and sigma star 1s. And then these 2 electrons go to fill the sigma 2s molecular orbital, and then we have none that are in the sigma star 2s. So what is our electronic configuration here? Well, it's sigma 1s squared, sigma star 1s squared, sigma 2s squared. And then if we go to calculate the bond order is going to be 1/2 here, because we have 4 electrons that are in bonding orbitals, these ones, and then we have 2 electrons that are in anti-bonding orbitals, these ones here. So that gives us the bond order of 4 minus 2 divided by 2. Oh, actually, sorry, this gives us a bond order of 1, not of 2, not of 1/2. So here we have a bond order of 1 for the molecule of lithium, molecular lithium. Now, normally lithium in its vapor phase will form stable molecules. The reason we don't normally list it as a diatomic molecule is probably because we don't usually think about lithium vapor all that often. We usually think about lithium existing as a solid. So at normal conditions, lithium is not a molecule. So this only usually occurs for when it's in the gas phase. But we can nonetheless predict it. If we go on to add 1 more electron, how does that affect the stability of the lithium ion? Well, what we're going to do is we're going to add 1 more electron. So this negative charge means we add 1 electron. That can go to either the left or the right side. I'll add it always to the left side just for simplicity. These will, the bottom electrons will occupy sigma 1s and sigma 1s star. And then because we have 1 extra electron, we need to occupy the sigma star 2s molecular orbital. Let me see if I can copy this. All right, now we're going to just add 1 extra molecular orbital here, the sigma star 2s. And that'll go to the first power. And that's destabilizing. So the bond order for this molecular ion, bond order, is 4 minus 3 divided by 2, which is 1/2. So by adding one extra electron, we end up destabilizing this molecule. We could also look at the lithium plus molecular ion, which would also destabilize the bond order by 1/2, because it would be removing an electron from a stabilizing bonding orbital. You can practice that one. All right, for the beryllium molecule, we'll see that all of the molecular orbitals are going to be filled. So beryllium has 4 electrons. Between the two of them, there'll be 8 electrons. 2 go into these stable and destabilizing molecular orbitals, and then we do the same thing for these ones up above. And whenever you have a situation like this, the bond is not likely to form because we essentially, all the energy that we've gained, we've lost by adding in the same number of electrons into anti-bonding orbitals. So here we don't predict that molecular beryllium is going to be stable. We predict it's going to be unstable. All right, so here we have a theory for why some molecules don't exist and why some molecules do exist. This is very powerful. We need to practice this with a few other examples. So let's look at the homonuclear diatomic molecules for elements that have p orbitals in a ground state. So carbon, let's see if carbon wants to form bonds with other carbon molecules or carbon atoms. So let's just look at the valence electrons here, because from above we can see that all of these don't matter when we're trying to figure out the bond order, because the 1s molecular orbitals will always cancel when we're in the second period. So let's just look at the valence electrons, and carbon has 4 valence electrons, 1, 2, and then we can really put these in any order, 3 and 4. And then, because I've already combined these into molecular orbitals, so it doesn't really matter at this point where those electrons are. And then the other carbon atom will have, that's the wrong direction. 2 electrons spin up over here. So the first 4 electrons are going to combine to give us sigma 2s and sigma star 2s molecular orbitals. And then the 4 other electrons are going to fill up the doubly degenerate pi 2px and pi 2py molecular orbitals. And then we can calculate what the most likely bond order of this is going to be. Well, here we have, let's see, how many? Okay, so I'll put all the bonding orbitals here in green, and then the anti-bonding in red. And we'll be able to see that we have 2, 4, 6 that are bonding, and then 2 that are anti-bonding. So the bond order for molecular carbon is a bond order of 2. I want to check my textbook, make sure that's right. Should be. Yep, that's correct. And it has a bond length of 124 picometers and a bond energy of 1.01 attojoules. Okay, cool. And then we could also write out the configuration here. This is good practice. So we have sigma 1s star, which is not, or sigma 1s squared, which is not shown here, but it's within the core. Sigma 1s star squared, sigma 2s squared, sigma star 2s squared, and then we have pi 2px and pi 2py, which I'll just write pi 2p to the fourth. All right, let's look at diatomic nitrogen. So nitrogen has 5 valence electrons for each nitrogen, so a total of 10 that we need to distribute across these molecular orbitals. So we can go ahead and put 1 electron in each of the 2p atomic orbitals, combine them to get these molecular orbitals, and see where they all end up. So 2 of the electrons are going to go down here, 2 up there, and then at this point we can fill up the degenerate pi 2p orbitals, and then we have 2 electrons left over, which will go into a stabilizing sigma 2pz molecular orbital. All right, so in this case, we end up getting a molecule of nitrogen that's going to have a lot of stabilizing interactions. So it's very favorable for nitrogen to come together with another nitrogen, because now all we're doing is adding in the sigma 2pz, or you could just write sigma 2p electrons. So then this gives us a bond order of, let's see, 2, 4, 6, 8, 8 minus 2 divided by 2, which is 3. So it gives us a bond order of 3, meaning we get a triple bond whenever nitrogen comes together with another nitrogen. And then we can look at the example where we have diatomic oxygen. And oxygen is a very interesting molecule to study with molecular orbital theory. So oxygen is going to have a total of 12 valence electrons. So we'll go on the left side here, we'll have 2, 3, 4, 5, 6. And then on the other side, another 6. And the first 4 electrons are going to go down here, and the sigma 2s and sigma star 2s. Now note, the molecular orbital sigma 2pz has gone lower in energy than the degenerate orbitals. So that's one small change here to this diagram. But then these fill up, all the same as nitrogen do. Really, the energy levels just switched a little bit. But then at this point, we've only used up 6 of those 8 electrons in the 2p atomic orbitals. So we need to put in 2 electrons up here, and note that they're going to go in different orbitals. So the sigma 2px and sigma 2py star molecular orbitals will have 1 electron in each of them. And this is really interesting because it gives rise to a property of molecular oxygen where it's magnetic. If you take a magnet and you pour liquid oxygen over it, you'll find that the oxygen will actually be attracted to the magnet because each of these electrons that are up here are unpaired. And if you remember from earlier in the lessons, I think it was in lesson 9, we talked about paramagnetism and diamagnetism, and that also applies to molecules. So in this case, this is an indication that oxygen is paramagnetic, because it has two unpaired electrons in its molecular orbitals. Also, part of the reason why oxygen is very reactive. It's a very strong oxidizing agent. And it points out a kind of fundamental limitation of drawing Lewis structures, because for Lewis structures, we don't see these molecular orbitals. We just see dots around the atoms, and we don't really know where those electrons are. We're just assuming they're being shared or unshared, but really they're all being shared. That's the kind of weird thing, right? So there's really no localized electrons anymore. They're a part of both of the atoms. So we have sigma star 2px to the first and sigma star 2py to the first. Bond order here, we can calculate it, and we'll get that it's 8 minus 4 divided by 2, or a double bond. Now, normally we would draw oxygen like this, which I drew. This is how I drew it up above. But compare it to this diagram, and you'll see that all of these electrons are shared. So really, these delocalized electrons, these electrons that we show here as lone pairs are in fact being shared in some ways. And that is kind of a limitation of Lewis structures. Okay, so that's the first half of this lecture on molecular orbitals. One thing I didn't go into in this lesson is how do you form molecular orbitals greater than the second shell. So when we get to something like sodium, now you can make use of the 3s molecular orbitals, as well as the 3p and even the 3d molecular orbitals. So those do exist, and we're not going to go into those in this class. You could learn about that in an inorganic chemistry class. And then additionally, we didn't talk about heteronuclear molecules, meaning what about when nitrogen and oxygen combine together? So that can happen as well. The only difference is these energies are all relative, and this can be seen in your textbook. There's a couple examples of that where it'll shift the energy levels slightly, but that's a little outside the scope of this class and outside of my experience, really. So I don't know how to explain that all that well. And then that's, I think, pretty much all you need to know at this point for molecular orbitals. All right, so that was explaining why some molecules form. But why do molecules take the shapes that they do? Well, we can't use molecular orbital theory to understand this phenomena, but we can make use of valence bond theory, which looks at localized covalent bonds as the result of the pairing of unpaired electrons in localized bond orbitals. Well, that's a mouthful. Well, this theory here is going to help us understand why certain chemical bonds have properties such as average bond lengths, average bond angles, and average bond energies that are consistent from molecule to molecule. We can see here on the right a methane molecule, CH4, where there is this overlap of these hybrid orbitals, which we're going to call sp3 orbitals, with the 1s orbital of a hydrogen atom, giving us 4 localized bond orbitals. So not anymore are we talking about delocalized orbitals, where 2 electrons will pair up to give us a configuration where each of these bonds is at the vertex of a tetrahedron, and these have a consistent 109.5 degree angle. So we'll have to start by looking at how do these hybrid orbitals form, and I'll get into that. Let's review what sigma and pi bonds refer to. We don't know what a sigma bond is. We've talked about sigma orbitals, and sigma and pi bonds result from the overlap of sigma orbitals or pi orbitals. So if we have some symmetrically symmetric orbitals, such as the hydrogen 1s orbitals, and they combine, we'll get a cylindrically symmetric bond where the energy density is between the nuclei. So we have the electrons being shared between the nuclei. We can also have that occur with these hybrid orbitals that I'm going to introduce, such as the sp3 and the 1s, so they can combine head-on, giving us a sigma bond. And we could also have a sp3 and an sp3 hybrid orbital combining head-on to give us the overlap that's symmetric in the plane of the nuclei. Now, another type of bond that can occur is a pi bond, where the electron density is in two lobes that are on either side of the bond axis. What we're looking at here is just the purple or the magenta colors here, where we have the electron density above and below where the nuclei are. Shown here is a sigma orbital, but the pi orbital here is the top and the bottom portion. They're arranged side by side, and pi bonds are really crucial because they restrict the motion of a molecule, so they prevent it from turning. So you had to break pi bonds in order for a molecule like this to be able to rotate. And they give rise to double bonds and triple bonds. One shorthand here that's going to be really helpful for you to learn how to understand hybridization is to think about that a single bond is always going to be made up of one sigma bond, whereas a double bond is going to be made up of one sigma bond and one pi bond. So right here, we can see a double bond shown here. Even though it looks like there's two pi bonds here, this is just one pi bond. It's on each pi bond has a lobe on both sides. So I'll just get rid of that pi symbol there. And then a triple bond is made up of one sigma and two pi bonds. The representative bond lengths and energies for the single, double, and triple bonds of carbon and nitrogen and oxygen are shown here. Anytime we measure a carbon-carbon bond, it's around 1.54 angstroms in length. And this has to do with the fact that these carbon-carbon single bonds are the result of sigma bonds overlapping. And they often have the same lengths, though this can vary from molecule to molecule. So let's look at how do I make hybrid orbitals and why this is necessary. Why can't we just use regular atomic orbitals, or why can't we just use molecular orbitals? Well, I think it's easiest to start with some examples in the second row hydrides. So if we look at the simplest hydride, which is beryllium hydride, we can start with thinking about beryllium having the electronic configuration of 1s2, 2s2, and hydrogen having the configuration of 1s1. Well, at the beginning, I talked about how valence bond theory looks at localized covalent bonds that result from the pairing of unpaired electrons. If we look at the electronic configuration of beryllium, it's got all paired electrons. So how can beryllium have a bond with hydrogen? Because normally I've been drawing beryllium like this. Why have I been drawing beryllium like this when it should really look like this based off of its electronic configuration? Its two valence electrons are paired up, right? So why have I been drawing it like this, and why have I been drawing it on either side? Well, I have kind of been working at this from the assumption that valence bond theory is correct and that the electrons for beryllium will want to bind on either side to give us a bond angle that looks like 180 degrees, and that we do form these molecules, right? So how can we make sense of going from this to that? That's really the question here. Well, Linus Pauling was one of the chemists that was really interested in studying this and helped popularize this idea of valence bond theory. His workaround was first that we need to promote an electron. So I've talked about excited states of molecules. Essentially, we need to excite the beryllium atom so that one of its electrons goes into a 2p orbital. We'll say that the 2p orbital that will be occupied is the 2pz. That's a little arbitrary. Again, I'm just defining the z-axis is where the nuclei are. So if we excite, so let's look at the electronic ground state of beryllium. So beryllium has 2 electrons. So the electron ground state is this. What we need to do is promote one of those electrons. So this one here in red is promoted. And then at that point, we have 2 orbitals that have unpaired electrons, and those electrons can go to combine with hydrogen 1s atomic orbitals to form a localized bond orbital. There is a problem with this, though, because if a 2s orbital combines with a 1s orbital, and then a 2pz orbital overlaps with a 1s orbital, we'd end up getting different bond lengths and the incorrect angles, because a 2s orbital is spherical, and then a 2p orbital is dumbbell shaped. Let's see if I can. And then because these will exist on the same atom, what we would end up getting is this type of a configuration. So we'd have the 2s atomic orbital of beryllium and its 2p molecular orbital, 2pz atomic orbital combining with hydrogen, and the hydrogen 1s would go here, and then we'd have another one that's trying to combine with the other orbital, which is spherically symmetric. So it wouldn't work properly. And the only way to rationalize this, Pauling came up with, was that these 2s and 2pz orbitals will actually hybridize together to give us 2 new orbitals that are going to be referred to as the sp hybrid orbitals. And then these 2 electrons will have the same energy. You'll see kind of they met in the middle. So the 2s went up and then the 2pz went down. So these are a little bit higher in energy. But then this will allow us to get proper bonding between the beryllium atom and the hydrogen atoms. How does this look like when we hybridize? Well, I have a depiction here. The 2s atomic orbital of beryllium will combine with the 2pz atomic orbital in 2 different ways. So it can combine with a positive phase on the left, or or we flip that. So we can flip that orientation. So what we end up getting is one hybrid orbital that has most of the electronic density along the negative z-axis, and then one along the positive z-axis. So here we can see we form 2 sp hybrid orbitals that are 180 degrees apart. There is going to be this small negative component, which I'm going to usually get rid of. So I'm going to show when these 2 orbitals combine, 1 and 2, they'll combine to give us this picture where we have two sp hybrid orbitals that are 180 degrees apart. So here I've gotten rid of the small negative charge. And this is going to allow us to get the correctly predicted geometry from Vesper theory of a linear electronic geometry. And one thing to keep in note here is that we only used two of the orbitals. There still are these unhybridized 2px and 2py orbitals, which we can add to the picture. This makes it look a little bit more complicated, but we'll use this image here later on to understand how double bonds and triple bonds form. So 2px and 2py orbitals are unhybridized, and they can still participate in pi bonding, not for beryllium, but for some other atoms. All right, so the thing we got to keep in mind here is what geometry do we want, and how do we make orbitals that will fit that geometry? All right, so let's move on to the next hydride in the second period, which is boron trihydride. And boron trihydride, if we draw the Lewis structure, will look like this, where we have three hydrogens, and they have a single bond each to boron in the middle, and then boron has a deficient octet, so it only has 6 electrons around it, not 8. It's one of the exceptions to the octet rule. And I've drawn it so that the bond angles here are 120 degrees away from each other. This is because this is the geometry that's predicted by Vesper theory. We want to have a trigonal planar geometry. So that's from lesson 12. But how can we have this type of a geometry when the electronic ground state of boron looks like this? Well, first thing that we need to do is we need to have 3 electrons that are unpaired that can combine with the 1s orbitals. So what we'll do is we'll promote one of those electrons to 2px. That'll be the next one we fill. That's just the way that the textbook has been doing it. 2pz, 2px, then 2py. And then we can combine 3 of those orbitals together to form 3 hybrid orbitals. And because we're combining one s orbital and 2 p orbitals, we get sp2 hybrid orbitals. And each of those hybrid orbitals will have 1 electron, which can combine with the hydrogen atoms. And what we'll get is an sp2 1s sigma bond that occurs between the borons and the hydrogens. So that's the sigma bonds that are occurring. We can draw that. First, let me show you what the hybridization looks like. So we have 2s, 2pz, and 2px coming together, 3 atomic orbitals giving rise to 3 hybrid orbitals, which the only difference in these orbitals is their orientation. I try to draw them so that they look like they're 120 degrees apart. These orbitals are going to exist along the xz axis, so they're going to have no component along the y. It looks like there's some small component here, but that's not. These are supposed to be drawn in the xz plane. And then what will end up happening when we combine these 3 orbitals together, we'll get some type of electronic configuration that looks like it's trigonal planar. And that's what we need to get the correct geometry. And then that leaves us with the 2py atomic orbital that's unhybridized. And if we want to include that along this image, we can show that along the y-axis. And this can participate in pi bonding to give us double bonds. So boron's not going to form double bonds, but some other elements will. And then if we wanted to draw, I can show you this. So if we take this image, and I'm just going to get rid of the axes here. if I put hydrogen atoms here, let me get rid of the plus charges. Okay, so these would be your hydrogen atoms. And then in the middle is your boron. And then the sigma bonds are the sharing of the electrons here. One electron from the hydrogen 1s orbitals. And then which are these? And then the overlap from the sp2 hybrid orbitals here. And so this is your sp2. And we get, and these are 1s. So we get sigma bonds, which result from the overlap of of a hybrid orbital with a 1s orbital. So we're going to get these sigma bonds that are occurring here. So 3 sigma bonds, 1, 2, and 3. All right, so if we look at the next hydride, that's CH4, also known as methane. This also appears to be incorrect, meaning we are unable to form localized atomic orbitals because we end up having electronic ground state where we have 2 electrons that are unpaired. So these 2 can combine, but these 2 electrons are unable to combine. We need to first promote them. So we'll promote one of those electrons, and that'll get promoted to the 2p atomic orbital. And then at that point, those will all have different energies. So in order for us to have the correct geometry, those orbitals need to combine to give us 4 equivalent sp3 hybrid orbitals. They're only going to differ in their orientation. So we can see that their orientation are going to be 109.5 degrees apart from each other. So they're going to be on the end of these orbitals is going to be on the corner of a tetrahedron. That's the furthest so that we can separate these atomic orbitals so that their electronic densities are as far away from each other as possible. And if we combine all 4 of those atomic orbitals onto one image, it's going to look somewhat like this, where we have 4 lobes of positive density that can combine with other atomic orbitals or other hybrid orbitals to participate in covalent bonding. So here we get the tetrahedral electronic geometry. And because we've used all of the atomic orbitals, there will be no unhybridized orbitals available, meaning we're only going to be able to participate in sigma bonding with sp3 hybridized atoms. Now, the rationale that Pauling provided for why electron promotion and hybridization is needed and why it's possible is that the formation of bonds provides the energy that's needed to overcome the energy you would need to put in to promote an electron and to hybridize those atomic orbitals. And we're going to specify bond types here using sigma and pi. For example, for methane, we can talk about the sigma bond that occurs between the sp3 hybrid orbitals on carbon with the 1s orbitals of hydrogen. If we look at ammonia and water next, ammonia has the structure of NH3 with one lone pair on the one lone pair on the nitrogen. And if we think about what electronic geometry is needed here, if we look back at lesson 12, we'll see that ammonia has 3 atoms attached and one lone pair. So we need to have a tetrahedral geometry for ammonia to take the correct angles between these hydrogens, because these hydrogens are going to be slightly less than 109.5 degrees. So what we're going to do for ammonium is we're going to also do the hybridization, but what we're going to need is sp3 hybridization. I can take one of these diagrams here. Same thing. All right, so for ammonia has, let's see, 5. So nitrogen has 5 electrons, and it's in the ground state like this. Electron promotion isn't needed for this molecule because there's already 3 electrons that are available for bonding. So promotion is actually not necessary here. However, the bond lengths all need to be the same, so we still need to hybridize. And when we hybridize, we'll end up getting 2 electrons that are in one of the hybrid orbitals. So these here represent your lone pair electrons. And then the other electrons listed here are going to be the ones that bind with the hydrogens. You can draw the structure here with nitrogen in the middle, and I'll draw 4 lobes. And then that one doesn't look so good. And then on one end of the lobes, we'll draw in the 1s orbital for hydrogen. And then with that one hybrid orbital, we can draw in the lone pairs. So we can draw a lone pair there. And then here's our hydrogens. And we can indicate that the electrons are being shared right there. And this would be one way you can depict the valence bond theory picture of ammonia. Here we can see these are 109.5 degrees away from each other. And the bonds themselves are going to be sigma, nitrogen sp3, hydrogen 1s bonds. Okay, and there's 3 of them here. And then there's one lone pair electron that's in a sp3 hybridized orbital here. All right, the last hydride I want to talk about is water. So let's do the same kind of thing with water. So water has the structure of a bent geometry, which is also an electronic geometry that is, if we can see here, it's bent shape, but its electronic geometry is tetrahedral. So what we're going to want to do for this hybridization theory is look at just the electronic geometry that's needed. So we'll need to have sp3 hybridization. If we look at the ground state for oxygen, we'll see that promotion, again, isn't necessary. And that's because there's 2 electrons that are unpaired, which can participate in bonding. However, you still need to hybridize, and we end up getting 2 lone pair electrons, and then 2 electrons left over for bonding with hydrogen. We end up getting the oxygen here in the middle. We'll get 2 lone pairs. I'm going to draw them like bunny ears. And then we have those remaining hybrid orbitals that are going to combine here with the 1s orbitals of hydrogen. And we now have the correct geometry for water. All right, so I'd like to go over a few cases where we can look at double and triple bonds. I think these are really helpful for visualizing, and they're a little bit more complex. So let's start off with an example like ethylene. Ethylene has 2 carbons, and we'll draw the Lewis structure for all these first, and 4 hydrogens. So when we try to distribute the electrons here, which we have a total of 12 valence electrons, 8 of them are going to go in the bonds, and then the other 4 electrons are going to be shared between the 2 carbons. So in this case is a first example of a double bond. How do we use valence bond theory to depict double bonds? Well, what we're going to need to do is think about what is the hybridization necessary here. For us to get a pi bond, we're going to need to have one unhybridized atomic orbital, and that occurs when we have sp2 hybridization. So we'll need sp2 hybridization on both these carbons, and I can actually just take the picture from up above. So let's take a look at this image here. And what I want you to picture is each of these images is one carbon. So I have the first carbon on the left, and then I have another carbon, and I'm going to flip this image. And I'm going to erase the axes here so we can see this better. Okay, so we have my first carbon, my second carbon coming together, and the sp2 hybridized orbitals will overlap in this region, and then we'll have these unhybridized p orbitals which will overlap like this to give us our pi bond. So we have a sigma bond, and then we have the pi bond. So that's how you form a pi bond. And then the rest of the orbitals will combine with the hydrogens on the end. And we get our molecule. So that's a fun way to depict ethylene. There we go. Okay. And then we don't need to have the positive and negative charges. They're a little unnecessary for the hybrid orbitals. So I'm going to get rid of those. I think I'm going to leave them for the p orbital so you can see those ones clearly. And then each of the carbons is represented right here. So here's your carbon 1, carbon 2, and then we have our hydrogens. And then there is 2 electrons here, 2 electrons here, 2 electrons there, there, and then there's 2 electrons in the sigma bond, and then 2 electrons in the pi bond. They could, let's say one's in the top, between the top lobes, and then one's in the bottom, between the bottom lobes. Awesome. So if we want to depict each of these different bonds that is occurring, we have the sigma carbon sp2 comma hydrogen 1s overlap. We have the sigma carbon sp2 carbon sp2 overlap, as well as the pi carbon sp2, py carbon py or 2py or overlap. Sorry, these are tricky to write out. 2py carbon 2py overlap. So we have three different types of bonds that are drawn here in this image. All right, let's look at acetylene. So acetylene is composed of 2 carbons and 2 hydrogens. So in a sense, it's a simpler molecule, but now we have a triple bond that's going to occur. So let me draw this a little closer. And when we want to get this geometry, we got to think, what's the bond angle between the carbons and between the carbon and the hydrogen? Well, we need to have 180 degrees. So this would be in a linear electronic geometry, which requires that we have sp hybridization on these carbons. And when we have sp hybridization, if we look back up here, we see that we combine the 2s and the 2pz atomic orbitals, giving us 2 sp hybrid orbitals, leaving these 2px and 2py orbitals unhybridized. These are what are going to contribute to the triple bond of acetylene. So let's look at what that looks like. So I included this already down here. This is going to represent my first carbon, and this is sp3 hybridization, where we have the unhybridized 2px and 2py orbitals. All right, let me get another one of these. All right, now when these 2 carbons come together, their sigma overlap occurs between the hybrid orbitals, and then we end up getting the triple bond that is going to occur between, how did I do up above? I just used black. All right, so we have the overlap occurs here between the positive phase and the negative phase on the 2py orbital, just like above. But then we also have the phase that occurs between the 2px positive and negative lobe. So here we have 4 different lines that are occurring. So the top set, the top and bottom set here, this is the first pi bond, and then we have another pi bond. So 2 pi bonds and a sigma bond. So this is what gives rise to the strength of acetylene's bond. That's because we have 3 different bonds that are overlapping in that same region. And then if we want to describe the bonding that's occurring here, let me first add the hydrogens. So hydrogen 1 and hydrogen 2. All right, we'll start with the hydrogen bonds. We have a sigma bond that occurs between the carbon sp hybrid orbital with the hydrogen 1s. We have the sigma bond between the carbons, which is a carbon sp overlap with a carbon sp overlap. And then we have the pi bonds, which occur between the carbon 2px and 2px, and then the overlap between the carbon 2py and 2py. One thing you might wonder is, why don't the 2px and 2py overlap? Well, they're perpendicular to each other, so they're not going to have much region that they overlap in. So we only get favorable interactions like this. And so here we have a triple bond. Wow, cool. So how do we make use of valence bond theory? Well, here's some examples where we have some complex molecules, and it might be helpful for us to understand what the hybridization on each of these atoms are. So let's go through 5 examples, and then I will show you how we can make hybridization between d orbitals. To begin with, you need to know what the hybridization on a given atom is. You can look at the number of bonded atoms that atom has, plus the number of lone pairs, to determine how many hybrid orbitals you're going to need for that molecule. This is a little bit of a simplification, but this is going to work for what we need it for. If we have two hybrid orbitals that are needed, either two bonded atoms and 0 lone pairs, or one bonded atom and 1 lone pair, like carbon monoxide, for example, we would need sp hybridization. We need to have 180 degrees in our bond, and that would require sp hybridization. If we have 3 hybrid orbitals, we need sp2. For 4 hybrid orbitals, it's sp3. And then I'll talk about this in a minute, but if you need 5 or 6 orbitals, you can make use of the d orbitals, and that would be sp3 d and sp3 d2. For this class, we're not going to consider the single bonded terminal atoms as hybridized. All right, so we'll just consider those to be unhybridized atoms, where whatever electrons that are available in its electronic configuration will be bonded. Let's look at this example. I have 3 butyne 2-ol, 3-butyne-2-ol. It's a hard one to say. Which has 4 carbons, 1 oxygen, and it has 6 hydrogens. Okay, so 3 of the hydrogens are on a carbon down here in the bottom left, and then there's a carbon here that has a single hydrogen, which is involved in a triple bond, and then we have a hydrogen bound to an oxygen, and then a hydrogen bound to a carbon here. So what I want to know for this is, what are the hybridizations of each of the carbons in this molecule, as well as the oxygen in this molecule? Well, if we start here at the bottom left, this carbon has 4 bonded atoms to it and no lone pairs. So this carbon is going to make use of sp3 hybridization. It's going to need 4 hybrid orbitals. And that's all you really need to know a lot of the time, is what is the hybridization on that carbon. The next carbon we're going to look at also has 4 atoms attached, so it's going to be sp3 hybridized. If we look at the next carbon, it's got only 2 atoms attached. In that case, this needs to be sp hybridized. That's the same case for this carbon over here. This is going to be very similar to acetylene right up above. It's going to have that triple bond made up of 2 pi bonds and 1 sigma bond. And then if we look at the oxygen here, this oxygen is going to have 2 atoms attached and 2 lone pairs. So this has to be sp3 hybridized. And then we're not going to hybridize any of the hydrogens. Those will just be all 1s orbitals. Wonderful. So that is the hybridization of each of those. I also want to know actually about how many sigma and how many pi bonds there are in each of these molecules. So we'll start by looking at the number of sigma bonds. That's going to be literally every bond. Every bond has at least a sigma bond. So the 3 hydrogens on the bottom left, let me draw this in yellow. So 1, 2, 3 sigma bonds. This carbon-carbon bond is going to be a sigma for 4, 5, 6, 7. So all these have to be sigma. This oxygen-carbon bond is going to be sigma, 8, 9. And then one of the triple bonds is going to be a sigma as well. So if you're counting there, that should be 10. And then because we have a triple bond here, triple bond needs to have 2 pi bonds. We'll have a total of 2 pi's. All right, the next molecule I have for us to look at is caffeine. So caffeine is a little more complex. It's got a lot of nitrogens and oxygens and carbons and hydrogens. So let's start by looking at some of the hybridizations on these terminal carbons. So this carbon on the outside has 4 atoms attached, 3 hydrogens and a nitrogen. So this is going to need sp3 hybridization. That's going to be the same case for all of these terminal carbon groups. These are called methyl groups. They resemble methane, but they're like a substituent group, so they're called a methyl. And then we can look at all of the atoms that are in this ring system. The oxygens are going to be terminal, so we're not going to look at their hybridization. And what we're going to do is we're going to simplify this here. We're going to say that these electrons here are going to require a hybrid orbital to be in. And that's not entirely correct, but for this class, again, it's okay. So we have 1, 2, 3 atoms attached, and then a lone pair. So this would be sp3 hybridized. And then this nitrogen, by that rule, would also be sp3 hybridized, as well as this nitrogen down here. And then this carbon on the bottom left has 3 atoms attached, so that's going to be sp2. And all of the carbons are going to be sp2 in this ring system. So we got a lot of sp2 hybridized orbitals, and this nitrogen down here will also be sp2. It's got 2 atoms attached in a lone pair. For reasons of resonance, these that I listed as these other nitrogens that I listed in this ring system that I listed as sp3 are actually sp2 orbitals due to resonance effects, but we'll worry about that right now. All right, so I'm going to redraw this caffeine molecule so we can look at it with and without the labels. Because what I want to know next is how many sigma and pi bonds it has. And having all those there might be a little distracting, so get rid of those. And we'll start by finding all the pi bonds would probably be the easiest thing to start with here. So a pi bond is anytime we have a double bond, we're going to add 1 pi. So I'll draw that here in blue. So we have a double bond there, a double bond here, a double bond here, and a double bond here. So those double bonds are going to require us to have 4 pi bonds. But each of those double bonds also has a sigma bond in it too. And so when we're going to also have to count those for the sigmas. So 4 right there. And then we'll count every other bond that's in caffeine. So we'll do 4 there, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So 24 sigma bonds in caffeine. Quite a few. Let me double count that. Okay, I got 24 again. Then I got one other complex molecule. This is histidine, which is one of the amino acids that's essential for life. Histidine has this nitrogen-based ring system here. That's a side chain. It's got an ammonium and a carboxylate functional group on it. And it also has these a variety of sp3 and sp2 hybridization that's needed. So we can start by doing the hybridization. This nitrogen that's here is going to be sp3 hybridized. It's got 4 atoms attached. This carbon at the top has only 3 atoms attached, so that's going to be sp2. And then we have sp3 and sp3 hybridization for these carbons because they have 4 atoms attached. And then down in this ring system, you can see a variety of of sp2 and one sp3 nitrogen. But again, for concept of resonance, all of these are actually going to be sp2. So let's just say sp2 for all down here. So you could if you draw a resonance structure, you'll see why it's actually sp2. The electron that's in this on this nitrogen is not actually localized on that nitrogen. It's delocalized with this carbon down here, and that can only occur when those electrons are in a pi bond. All right. So how many sigma bonds and pi bonds do we have here? Well, we have. Let's start with the double bonds. It's 1, 2, 3. So there should be 3 pi bonds, and then sigma bonds will be everything else. All right, I got 20 for histidine. So a little bit less complex than caffeine, but not by too much. And then these last two examples, well, I have xenon tetrafluoride and xenon difluoride, which are these molecules which don't, we can't just use sp, sp2, or sp3 hybrid orbitals. We need to now make use of d orbitals because they need to have 5 equivalent orbitals or 6 equivalent orbitals. So this image here of xenon tetrafluoride requires a square pyramidal shape, or is it square planar shape, which means it has to have octahedral electronic geometry. And then the other xenon molecule, xenon difluoride, has linear shape, which requires a trigonal bipyramidal electronic geometry. So in order for us to get those, that's when we need to make use of these d orbitals. And so this xenon here in the middle has sp3d2 hybridization. And then this xenon here has sp3d or hybridization. All right. We won't go into any more detail on sigma and pi for this one. But here's a little bit of a pictorial representation of how those d orbitals combine. We can make use of this donut-shaped dz squared orbital, combine it with the 3s and the 3p atomic orbitals of the third row to create 5 sp3d hybrid orbitals that are 120 degrees and 90 degrees apart. This gives us the trigonal bipyramidal electronic geometry. And then you can do the same thing, just add in one more d orbital, like, for example, the x squared minus y squared d orbital, which has lobes along the y and the x-axis. And then that'll give us 6 equivalent hybrid orbitals, which are called sp3d2 hybrid orbitals because they're made up of an s, 3p, and 2d orbitals, which will be 90 degrees apart from each other, where the vertex of each of these is on the corner of an octahedron, giving us the octahedral electronic geometry. Well, this has been a long lecture, and it goes into a lot of information about covalent bonding and why we get the molecular shapes that we do and why certain molecules form. I hope this was informative and you enjoyed this lesson. There's an extra credit assignment on this one, and it'll ask you about the stuff that I talked about in this lesson, but feel free to reach out if you have any questions. And and have a great day.